A galaxy's true ruler is completely invisible. What we see, the glittering stars and glowing gas, is just the decoration on a hidden framework of staggering power and mystery. That framework is a dark matter halo, an immense sphere of unseen mass that dictates how galaxies spin, form, and survive. It is the cosmic skeleton upon which everything luminous is built. Yet for all its importance, it remains one of the greatest enigmas in modern science. By the end of this exploration, you will understand 25 of the deepest, most perplexing mysteries surrounding these invisible giants, from ghostly galaxies made almost entirely of dark matter to the bizarre, structured planes of orbiting satellites. How can something we cannot see define everything we can? Our journey into the shadows begins with a glaring absence. Powerful computer simulations of cosmic evolution paint a very specific picture of our galactic home. They tell us the immense dark matter halo surrounding the Milky Way is not a smooth, featureless cloud. Instead, it should be a bustling metropolis of smaller structures, hundreds of dense clumps of dark matter called subhalos, each one a potential cradle for a tiny galaxy. The prediction is clear: our sky should be filled with the faint glow of countless dwarf galaxies orbiting our own. Yet when we look up, the reality is starkly different. We see only a few dozen of these small companions. This is the missing satellite problem, and it represents a fundamental crack in our understanding of how the universe builds itself. Where are the hundreds of galaxies that should be there? The answer forces us down two equally profound paths. Perhaps the simulations are right about the dark matter, but our understanding of galaxy formation is wrong. Those predicted subhalos might indeed exist, but they could be almost completely dark. Maybe the conditions within the smallest halos prevented gas from ever cooling and collapsing to form stars, leaving them as invisible, starless ghosts orbiting silently in the void. On the other hand, perhaps the dark matter itself is not what we think. Some scientists propose a tweak to the recipe, suggesting dark matter particles might be slightly warmer, moving faster in the early universe. This warmth would smooth out the smallest clumps, preventing those hundreds of tiny subhalos from ever forming in the first place, neatly explaining the quiet skies we observe. Others look to the violent astrophysics of the early cosmos. They suggest that in the smallest halos, the first bursts of star formation could have been so intense that their radiation and supernova explosions blew out all the remaining gas, starving the halo of the fuel needed to make more stars and leaving it permanently stunted and dark. This first mystery sets the stage for everything to come, revealing that the dark matter halo is not just a simple mass holding a galaxy together. It is a complex, structured entity with a history written in both what we see and, more importantly, in what we do not. This discrepancy between prediction and observation is not just a minor detail. It cuts to the very heart of what dark matter is made of, and it has ignited one of the most heated debates in modern cosmology. We call it the cusp versus core controversy. The most sophisticated computer models of dark matter halos running on the world's most powerful supercomputers all tell the same story. They predict that the density of dark matter should rise steeply, dramatically, as you approach the very center of a galaxy or a dwarf galaxy. Picture a mountain with an impossibly sharp peak. That peak is the cusp, a dense, concentrated spike of dark matter right at the galactic heart. This prediction comes directly from the leading model of dark matter, known as cold dark matter, where particles move slowly and interact with each other and with normal matter only through gravity. It is a clean, elegant theoretical result, but when astronomers train their telescopes on real dwarf galaxies, the faint, diffuse satellites of the Milky Way, and carefully measure how stars move within them, they often find something very different. Instead of that sharp peak, the data suggests a flat central region, a plateau. This is the core. It is as if someone took that theoretical mountain and sheared off its peak, leaving behind a rounded, gentle hill. The significance of this cannot be overstated. If the observations are correct and cores are common, it means our foundational model of dark matter is missing a crucial ingredient. One compelling explanation is that dark matter particles might not be completely silent and aloof. Perhaps they can interact with each other in ways beyond gravity. If dark matter particles can collide or scatter off one another, even very weakly, this self-interaction could act like a form of friction. Over cosmic time, this friction would smooth out the sharp central cusp, transferring energy from the densely packed inner particles to those farther out, eventually eroding the peak into a constant density core. It is a small tweak with monumental implications, suggesting a hidden richness to the dark sector. Yet there is another, equally dramatic possibility. Perhaps the cusp is formed as the simulations predict, but then normal matter, the stars and gas we can see, comes along and destroys it. Imagine the center of a young dwarf galaxy. The first massive stars are born, live violently, and die in colossal supernova explosions. These blasts unleash torrents of energy, pushing the surrounding gas outward with tremendous force. As this normal matter surges out, its changing gravitational pull could act like a cosmic spoon, stirring up the dark matter at the center and gradually scooping it out, transforming a cusp into a core through sheer astrophysical violence. So which force is the true sculptor? Is it an intrinsic whisper between dark matter particles or the thunderous aftermath of stellar death? This controversy remains unresolved, a testament to the fact that to understand the invisible halo, we must also decipher the complex dance it performs with the luminous universe it hosts. The cusp versus core debate shows us that the smallest galaxies hold immense secrets, but what about the ones that should have been giants? This leads us to a deeper, more puzzling layer of the satellite mystery called the too big to fail problem. Here, the conflict between prediction and reality becomes even more stark. Our most trusted simulations do not just predict hundreds of small dark matter clumps, they also forecast a handful of exceptionally massive subhalos. These should be the crown jewels of the Milky Way satellite system, dense and powerful enough to easily attract and hold onto vast amounts of gas. By all the standard rules of cosmic construction, these colossal halos should have blossomed into the brightest, most star-rich dwarf galaxies in our local neighborhood. They were simply too big to fail at the task of building a luminous galaxy. Yet when we census the dwarfs actually orbiting our galaxy, none of them match the predicted heft and splendor of these missing giants. The dwarfs we see are all far less massive and dimmer than what the simulations say should be there. It is as if the universe's most promising construction sites were abandoned, leaving behind only faint, skeletal outlines where majestic structures were meant to stand. So why did these behemoths fail? One leading suspect is a cosmic event called reionization. In the universe's first billion years, the first stars and galaxies flickered to life, flooding the cosmos with a brutal tide of ultraviolet radiation. This epoch of reionization sterilized the universe, stripping the fragile, neutral gas away from small, vulnerable structures. For these massive subhalos, the timing may have been catastrophically wrong. If they formed their stars too slowly, or if they lived in a region bathed early in this harsh radiation, their vast reservoirs of star-forming gas could have been blown away before they ever had a chance to use it. The halo remained massive and dark, but its potential for light was extinguished forever by an ancient cosmic dawn. Alternatively, the failure might once again point to the dark matter itself. If dark matter is warmer or has some other property that suppresses the very densest peaks of matter in the early universe, then these predicted massive subhalos may never have achieved their simulated density in the first place. They would be less concentrated, their gravitational grip weaker, making it easier for events like reionization to ravage them. this problem forces us to confront an uncomfortable truth. Our simulations are not just missing small galaxies, they are also creating the wrong kind of large ones. The invisible architecture of our halo appears to be both more complex and more subtle than our best virtual universes can currently replicate, hiding its greatest failures in plain, dark sight. These failures of prediction force us to look at the satellites we do have with a more critical eye, and their arrangement holds a surprise that is just as unsettling. The dwarf galaxies orbiting the Milky Way are not scattered randomly around us like a swarm of bees. A significant number of them, along with a similar group around the Andromeda Galaxy, are organized with an eerie precision. They are aligned in vast, thin, rotating structures, what astronomers call planes of satellites. Picture a giant, invisible vinyl record spinning slowly in space, with these small galaxies embedded in it like jewels on the groove. This is not what our standard model of cosmic structure predicts at all. In the lambda-cold dark matter universe, galaxies grow hierarchically through countless mergers and the steady accretion of smaller halos over billions of years. These captured satellites should arrive from all directions, their orbits chaotically oriented, creating a roughly spherical cloud around the main galaxy. Finding so many of them moving together in a coordinated disk is like throwing a handful of marbles into the air and watching them all fall into a neat spinning circle. The probability of it happening by pure chance is astronomically low, pointing to a fundamental gap in our story. One compelling explanation points to a dramatic event in our galaxy's past. Perhaps the Milky Way experienced a colossal merger with another large galaxy many billions of years ago. Such a violent encounter could have torn streams of stars and gas from the smaller victim, and within those tidal tails, new dwarf galaxies could have formed. Because they were born from the same event, from the same debris field, they would naturally inherit a shared motion, locked into the same plane like dancers spinning from a single, powerful toss. This is a galactic memory written in orbital paths, a fossil record of ancient chaos. Yet this tidy explanation faces its own challenges, especially when we see similar planes around other galaxies like Andromeda. Were they all shaped by such perfectly aligned, massive mergers, the coincidence begins to strain belief. This leads to a far more radical possibility. What if these planes are not accidents of history, but signatures of how the cosmic web itself delivers material to galaxies? In the early universe, dark matter and gas flow into growing halos along dense, narrow filaments of the cosmic web. It is possible that satellites form primarily within these great rivers of matter and are funneled into the central galaxy along the same highway. They would arrive not from random angles but from specific directions, potentially preserving a disk-like distribution. If true, this would mean the satellites we see today are not mostly captured strangers, but born and raised family members all arriving from the same cosmic thoroughfare. This mystery strikes at a core principle. The ordered planes of satellites stand in stark opposition to the predicted chaos of the dark matter halo. Do they reveal a violent chapter in our galaxy's biography, or do they point to a flaw in our understanding of how the universe builds its largest structures? The answer may force us to rewrite the story of our galactic home from its very first pages. The eerie order of satellite planes suggests a hidden structure in the cosmic delivery system, but when we look at the motion within galaxies themselves, we find a different kind of puzzle, one of bewildering variety. This is the mystery of the diversity of rotation curves. The very reason dark matter was proposed was to explain a single, stunning observation, that stars at the outer edges of spiral galaxies orbit just as fast as those near the center. Their speed does not drop off as you would expect if only the visible stars and gas were pulling on them. This flat rotation curve became the signature of the invisible dark matter halo, its gravitational grip holding the galaxy together. But as our telescopes peered at more and more galaxies, a complication emerged. Not all rotation curves are flat. In fact, they come in a startling array of shapes, and this diversity is a profound headache for anyone trying to build a simple model of the cosmos. Take the majestic spiral galaxies like our own Milky Way. Their rotation curves are typically flat, rising gently in the inner regions and then staying constant far out into the halo, a classic textbook case. Now look at the faint, wispy, low-surface brightness galaxies. These are ghostly spirals with so few stars they are barely visible against the night sky. Their rotation curves are different. They often rise very slowly, taking much longer to reach that flat plateau, as if their dark matter halos are more spread out and diffuse, less concentrated at the center. Then there are the dwarf spheroidal galaxies, the tiny satellites of the Milky Way. Their rotation curves, inferred from the motions of their stars, are not even flat in the same way. They suggest halos with large, constant density cores, not the steep central cusps the simplest models predict. Why would three types of galaxies, all embedded in dark matter halos, show three distinctly different patterns of motion? If dark matter is a simple, cold, and non-interacting substance that just clumps under gravity, you might expect a more uniform family resemblance. This wild diversity tells us that the relationship between the dark matter halo and the luminous galaxy inside it is not a simple one-way street. It is a complex back-and-forth dialogue spanning billions of years. The stars and gas are not just passive passengers, they are active participants. In a massive spiral galaxy, furious cycles of star formation and supernova explosions can pump energy into the center of the dark matter halo, potentially puffing it up or smoothing it out over time. In a faint, low-surface brightness galaxy, that stellar feedback may have been much weaker or more gentle, leaving the original shape of the dark matter distribution more pristine. The history of each galaxy, its unique saga of births and explosions and mergers, is imprinted onto the shape of its rotation curve. There is an even more radical interpretation of this data. Perhaps the diversity points to dark matter itself being more complex than a single type of particle. Could the dark sector have its own rich physics with multiple components that behave differently? Imagine if dark matter came in both a heavy, slow-moving form and a lighter, faster-moving variety. Different mixtures of these components could naturally give rise to the different halo structures we infer from the varied rotation curves. One galaxy might form in a region dominated by cold dark matter, yielding a dense, cuspy halo and a sharply rising rotation curve. Another might form where warmer dark matter is more prevalent, resulting in a fluffier halo and a slowly rising curve. This idea turns the dark matter halo from a simple mass into a potential ecosystem with its own hidden chemistry and history. The diversity of rotation curves is a clear message from the cosmos. The dark matter halo is not a cookie-cutter mold. It is a custom-tailored garment shaped by a long and intimate conversation with the galaxy it envelops, and perhaps by the very nature of the invisible substance from which it is made. If the diversity of rotation curves reveals a complex conversation, some galaxies seem to have given up speaking altogether. Drifting through the dense coma cluster of galaxies are cosmic phantoms known as ultra-diffuse galaxies. They are among the most perplexing objects in the modern sky. Take Dragonfly 44, a famous example. In terms of sheer physical size, it rivals our own Milky Way, spanning tens of thousands of light years. But that is where the similarity ends. Where our galaxy blazes with hundreds of billions of stars, Dragonfly 44 contains only about 1% of that number, a mere sprinkling of visible light. Its stars are so few and far apart that the galaxy is nearly transparent, a wispy ghost against the dark. Yet when astronomers measured the motions of those scant stars, they received a shock. The stars were whipping around at tremendous speeds that could only be explained if Dragonfly 44 was embedded in a dark matter halo as massive as the Milky Way's own. This means this ghostly giant is composed of roughly 99.99% dark matter. It is a dark matter halo that forgot to build a proper galaxy. How does such a thing even happen? How can a gravitational trap so powerful, with all the mass needed to forge a brilliant spiral, end up producing almost no stars? One theory paints a tragic picture of cosmic robbery. Ultra-diffuse galaxies like Dragonfly 44 are often found within the violent environments of galaxy clusters. As a normal galaxy falls into a cluster for the first time, it can plunge through the hot, thin gas that fills the space between galaxies. This intergalactic plasma acts like a torrential headwind, capable of violently stripping away a galaxy's cold, star-forming gas in a process called ram pressure stripping. Imagine a dandelion seed head blown by a strong gust, losing all its delicate filaments. The dark matter halo, unaffected by this gaseous wind, remains intact, holding onto the stars that had already formed. What is left is a massive dark matter skeleton with a skeletal population of stars, a failed giant whose future was stolen by its environment. But there is another, more serene possibility. Perhaps these ultra-diffuse galaxies are not failures at all, but triumphs of isolation. What if they formed in the quietest, most pristine corners of the early universe, in regions where the gas density was exceptionally low? In this scenario, the dark matter halo assembled normally, but the tiny amount of normal matter it captured was simply too diffuse, too spread out, to ever collapse efficiently and trigger widespread star formation. It would be a dark matter halo in its purest, most untouched state, exactly as predicted by simulations before any messy astrophysics begins. Dragonfly 44 and its kind would then be our clearest window into the raw architecture of a halo, a direct look at the cosmic scaffold with minimal contamination from the bright, complicated world of stars and gas. They are either the victims of a violent cluster or the reclusive, pristine aristocrats of the dark universe. This enigma forces us to ask a deeper question. Is a dark matter halo truly defined by the galaxy it holds, or can it exist as a complete, powerful entity all on its own? Those ghostly giants show us halos can exist almost alone, but to truly map their invisible form, we need to find something they have disturbed. Scattered throughout the halo of the Milky Way are not just dwarf galaxies, but long, shimmering ribbons of stars known as tidal streams. These are the cosmic aftermath of violence, formed when the immense gravity of our galaxy slowly pulls apart a smaller star cluster or a dwarf satellite. As the victim orbits, stars are stripped from it like grains of sand from a crumbling sandcastle, creating two elegant, trailing arcs that precede and follow the doomed object along its path. These streams are more than just beautiful relics, they are the most sensitive gravitational detectors we possess. Think of a single, perfect hairline crack across a vast pane of glass. Any tiny disturbance, any vibration, will alter that crack's path in a clear and measurable way. A tidal stream is that hairline crack drawn across the dark matter halo. The stars within it move with a predictable grace, following the smooth, overarching pull of the galaxy's total mass. But if a dense clump of dark matter, one of those predicted but invisible sub-halos, happens to pass nearby, its concentrated gravity will give the stream a subtle gravitational kick. It can warp the stream's path, stir up its stars, or even punch a visible gap in its stellar ribbon. By reading these delicate distortions, astronomers can do something astonishing. They can map the unseen lumps and bumps within the halo. This turns the streams into a kind of cosmic fishing line, trawling through the darkness and feeling for the tugs of hidden structure. The grandest goal of this fishing expedition is to determine the true shape of our dark matter halo itself. Our standard models often assume halos are roughly spherical, but they could be flattened like a rugby ball or even triaxial, having three different axes like a cosmic potato. The precise, galaxy-wide paths of multiple tidal streams, each feeling the halo's gravity from a different angle, should reveal this shape, A spherical halo would bend streams in one way, while a flattened halo would warp them differently. Projects like the European Space Agency's Gaia mission are revolutionizing this search. Gaia is not just mapping stars, it is creating a multidimensional movie of our galaxy, charting the precise positions, motions, and distances for over 1 billion stars. Within this incredible dataset, we are finding more tidal streams than ever before and measuring their stellar motions with unprecedented accuracy. We are essentially getting our first high-resolution scan of the halo's gravitational field. Yet here lies the core of the mystery. As we examine these exquisite stellar ribbons with Gaia's sharp eye, we are finding that many of them appear almost too perfect, too smooth. The expected gaps and kinks from numerous dark subhalos are not showing up as clearly as our best simulations predict. It is a quiet tension where the exquisite sensitivity of the probes seems to be revealing a halo that is, on large scales, smoother and more serene than we anticipated. Does this mean the hundreds of dark matter subhalos predicted by the simulations are simply not there? Or are they there but less massive or more spread out than we thought? Or are our streams still too young, not yet having encountered enough of these dark ghosts for the scars to show? Each pristine stream is a silent witness, and its very smoothness is deepening the puzzle of what truly lurks in the dark. The smoothness of tidal streams hints at a halo governed by hidden rules, and one rule in particular is so precise it borders on the mystical. Across thousands of galaxies, from the faintest dwarfs to the brightest spirals, a single, breathtakingly simple relationship holds true. For any star or cloud of gas within a galaxy, you can measure its observed orbital acceleration, how strongly it is being pulled by the galaxy's total gravity. You can also calculate the acceleration expected from just the visible matter, the stars and gas, at that same point. Plotting these two numbers against each other for countless points in countless galaxies reveals something astonishing. The points do not scatter randomly, they fall along a single, smooth, universal curve. This is the radial acceleration relation, a discovery so clean and powerful it feels like uncovering a fundamental law of the cosmos. It tells us that the acceleration due to dark matter is not random or independent. It is exquisitely tuned to the acceleration from normal matter. Where visible matter provides a strong pull, dark matter adds just the right amount of extra pull to reach the total. Where visible matter's pull is weak, dark matter's contribution is precisely calibrated to be weak as well. It is as if the invisible halo is constantly listening to the luminous galaxy and adjusting its own strength in perfect harmony. This perfect correlation is the heart of the mystery. Why does dark matter seem to know exactly how much normal matter is present at every single location within a galaxy? How does it arrange its own distribution to create this flawless mathematical lockstep? For proponents of an alternative theory called modified Newtonian dynamics, or MOND, this relation is not a mystery at all. It is the predicted result. MOND proposes there is no dark matter. Instead, the laws of gravity themselves change at the very low accelerations found in the outskirts of galaxies. In this view, the radial acceleration relation is the fundamental law, and the illusion of dark matter is just gravity behaving differently than Newton or Einstein predicted. The curve is the answer, not a puzzle to be solved. For the standard model of cosmology, lambda cold dark matter, this relation presents a monumental challenge. It is a cosmic conspiracy that the theory must explain. If dark matter is a separate, collisionless substance that clumps under its own gravity, why should its final distribution so perfectly mirror the messy, complex, and much later assembly of stars and gas? The leading explanation within lambda cold dark matter is that this is not a conspiracy but an emergent property. It is the outcome of the long, violent, and intimate dance between dark matter and normal matter over billions of years. In this story, the dark matter halo forms first, creating a gravitational well. Normal matter then falls in, but it does not sit quietly. it forms stars, those stars explode, and these supernovae pump enormous energy back into the gas. This energetic feedback pushes the normal matter around, which in turn subtly reshapes the gravitational potential, causing the dark matter to also move and settle into a new configuration. Through eons of this back and forth, the two components achieve a kind of equilibrium, a balanced state that naturally produces the tight relation we observe. It is not that dark matter knows, it is that the two have argued and negotiated until they reached a compromise. This makes the radial acceleration relation a critical battleground. Is it a sign that we need to rewrite gravity, or is it a stunning testament to the complex, self-regulating physics of galaxy formation? The curve itself offers no immediate verdict, only a profound clue that the universe operates with a hidden coherence, connecting the seen and the unseen with a mathematical handshake. The perfect harmony of the radial acceleration relation reveals a hidden order within single galaxies, but when we zoom out to the grandest scales of the cosmos, that order meets chaos on an epic scale. Our next mystery takes us to the titanic cities of the universe, galaxy clusters. These are not just collections of a few galaxies, they are immense metropolises containing hundreds, even thousands of them, all bound together in a seething ball of gravity. The dark matter halo of a single galaxy is vast, but the halo enveloping an entire cluster is almost incomprehensible. It forms a gargantuan, invisible sphere of influence millions of light-years across. At this staggering scale, we can finally see the dark matter halo, not by its light but by the warping of spacetime itself. This is the domain of gravitational lensing. The cluster's titanic mass, dominated by its dark matter halo, acts as a cosmic magnifying glass. It bends and distorts the very fabric of space, which in turn bends the paths of light rays from galaxies far behind it. To telescopes like the Hubble Space Telescope, this creates a breathtaking sight. The faint, distant background galaxies are stretched and smeared into brilliant arcs and faint, ghostly rings encircling the cluster's center. These Einstein rings and arcs are not just beautiful, they are a precise scientific tool. By meticulously measuring the exact shape and distortion of these lensed images, astronomers can create a mass map of the cluster's total gravitational field. It is a direct blueprint of the invisible dark matter halo, showing us where its mass is concentrated. This gives us the halo's true weight, but here is where the mystery deepens. We have two other completely independent ways to weigh the same galaxy cluster. The first looks at the hot, thin gas that fills the space between the galaxies. This intracluster plasma is heated to millions of degrees, so hot it glows not in visible light but in powerful X-rays. By observing this X-ray emission with space telescopes like Chandra, we can measure the gas's temperature and density. Since the hot gas is held in equilibrium by the cluster's gravity, its properties tell us about the shape of the gravitational well, giving us a second, independent map of the total mass. The third method is to simply add up the mass of all the visible galaxies themselves, though this is a tiny fraction of the total. In a perfect, simple universe, these three maps, the lensing map from bent light, the X-ray map from hot gas, and the map from the galaxies, should all align perfectly. They should all tell the same story about where the mass is, but they do not always match. Subtle, persistent discrepancies are emerging. Sometimes the lensing map suggests mass is clumped in a slightly different place than the hot gas map indicates. Other times, the overall masses derived from the two methods disagree by a small but significant margin. These misalignments are not errors, they are clues. One thrilling possibility is that they are evidence of dark matter interacting with itself. If dark matter particles can scatter off each other, even very weakly, this self-interaction would cause the dark matter halo to lag behind the normal matter during a violent event like a cluster collision. The dark matter, behaving like a subtle, diffuse fluid, would smooth out and shift, while the collisional gas would slow down and heat up, creating a detectable offset between the lensing mass map and the X-ray map. We may be seeing the dark matter's hidden social life. Another factor could be the ghostly neutrino. These nearly massless particles flood the universe, and they are produced in enormous numbers in the hot interiors of galaxy clusters. While individually insignificant, their sheer abundance means they contribute a small but measurable amount to the cluster's mass. Crucially, neutrinos behave differently than cold dark matter. They are fast-moving and rarely interact. Their presence could subtly alter the balance between the lensing and X-ray mass measurements in a unique way. Finally, the discrepancies might point to complexities in the physics of the intracluster plasma itself. Perhaps magnetic fields tangled within the hot gas or unseen turbulence are affecting how we interpret its X-ray emission, throwing off our mass calculation from that method. Each of these explanations points to new physics. The dark matter halo of a galaxy cluster is thus more than just a scaled-up version of a galactic halo. It is a cosmic laboratory. Within its immense volume, the three pillars of the cosmos, dark matter, hot normal matter, and relativistic neutrinos, all leave their distinct imprint on gravity and light. By reading the disagreements between our maps, we are deciphering a hidden conversation between forces that shaped the universe itself. The immense halo of a galaxy cluster is a cosmic laboratory, but the most crucial experiment in dark matter science is happening right in the heart of our own Milky Way. If dark matter is more than just a gravitational phantom, if it is made of real particles, then those particles might leave a trace of light. This is the search for dark matter annihilation, a hunt for the invisible halo's faintest possible glow. The leading candidate particle for decades has been the WIMP, the weakly interacting massive particle. As the name suggests, these hypothetical particles would interact only through the weak nuclear force and gravity, making them incredibly difficult to detect directly. But they hold a tantalizing promise. According to theory, when two WIMP collide in the dense core of a dark matter halo, they could annihilate each other, transforming their mass into pure energy and producing a shower of secondary particles, including high-energy gamma rays. The centers of galaxies, where dark matter density is predicted to be highest, should therefore be the brightest beacons for this annihilation signal. It is a simple and beautiful idea. Turn the halo's greatest concentration into our best chance to see it. For over a decade, the Fermi Gamma Ray Space Telescope has been scanning the sky for these telltale flashes, and it found something extraordinary at the very center of our galaxy. There is a persistent, diffuse glow of gamma rays emanating from the galactic core, an excess that does not perfectly match the expected emission from known astrophysical sources like pulsars or cosmic ray interactions. This is the galactic center excess, and for many, it felt like the moment of discovery. Here was a signal in the right place with the right energy profile, potentially matching the predictions for dark matter annihilation. The excitement was palpable, the idea that we were finally seeing the halo not by its gravity, but by its own self-destruction. Yet in science, extraordinary claims require extraordinary evidence, and this signal has been subjected to relentless scrutiny. The central mystery is one of interpretation. Is this glow the collective whisper of countless dark matter particles meeting their end, or is it simply a chorus of mundane astrophysical objects we do not yet fully understand? The most compelling alternative explanation is a hidden population of millisecond pulsars. These are the rapidly spinning, ultra-dense cores of dead stars, and they also emit gamma rays. Thousands of these faint, point-like sources, too dim for Fermi to resolve individually, could blend together to create a smooth, diffuse excess that perfectly mimics a dark matter signal. Distinguishing between a smooth annihilation glow and a grainy collection of pulsars is one of the greatest analytical challenges in modern astrophysics. The debate hinges on the statistical texture of the gamma-ray map, a pixel-by-pixel argument over whether the light is truly uniform or subtly clumpy. It is a high-stakes game of cosmic pattern recognition. This ambiguity is why scientists have turned to a different, cleaner type of dark matter laboratory, the dwarf spheroidal galaxies that orbit the Milky Way. These tiny satellites are considered pristine targets because they are, by galactic standards, boring. They have almost no gas, no recent star formation, and very few of the conventional astrophysical engines that produce gamma rays. What they do possess, according to our models, are extremely dense concentrations of dark matter. If dark matter annihilates anywhere, the signal from these quiet dwarfs should be unmistakable, a clear spike of gamma rays against a virtually silent background. Fermi has stared at these dwarfs for years, combining data from dozens of them to hunt for a collective signal. So far, it has seen nothing, no unambiguous excess, no definitive glow. The silence from the dwarfs is deafening, and it casts a long shadow over the exciting signal from our own galactic center. If dark matter is annihilating brightly in the Milky Way's core, why is it not doing the same in these pristine, dark matter-dominated dwarfs? The contradiction forces a difficult choice. Either the galactic center excess is not dark matter at all, but an unknown pulsar population, or our understanding of how dark matter is distributed within dwarf galaxies is fundamentally wrong. Perhaps their halos are less cuspy and more spread out than we think, lowering the annihilation rate. Or perhaps dark matter particles are not WIMP after all, but something else that annihilates in a way we have not yet predicted. This search, spanning from the bustling galactic downtown to the silent dwarf villages, captures the essence of the hunt. We are listening for a whisper that could rewrite physics, but first we must learn to distinguish it from the endless rustle of the cosmos. The silent dwarfs and the glowing galactic core present a contradiction, but they are just 2 points on a grand cosmic graph. Our models of dark matter make a profound prediction about the architecture of all halos, a prediction so fundamental it is known as the halo mass concentration relation. In essence, it states that the universe has a preferred way of packing dark matter. More massive dark matter halos, like those surrounding giant galaxy clusters, should be less centrally concentrated. They should have a fluffier, more spread-out distribution of mass. Conversely, the smallest halos, like those around dwarf galaxies, should be densest at their hearts, with matter packed into a sharp, steep peak. This makes intuitive sense if you think about cosmic history. The smallest structures are the ancient ones. They collapsed first when the universe itself was far denser, trapping dark matter into incredibly compact knots. The largest structures, like the great clusters, are the latecomers. They assembled only recently from the merging of many smaller pieces, resulting in a more diffuse, loosely bound final product. Supercomputer simulations of a cold dark matter universe show this relationship with beautiful clarity, a smooth, declining curve linking mass to concentration. It is a cornerstone prediction. The mystery lies in testing this elegant rule against the messy, real universe. Do the halos we infer around real galaxy clusters and real dwarf galaxies fall neatly on that theoretical line? The answer is not simple, and the deviations are where the physics gets interesting. When we look at the most massive galaxy clusters, we sometimes find they are more concentrated than the relation predicts. Their dark matter is packed tighter than it should be for an object of such immense size. This could be a sign of dramatic astrophysical intervention. As a cluster forms, it is not just dark matter falling together. Vast rivers of normal matter in the form of hot gas also flow into the gravitational well. As this gas sinks to the center, it can drag some of the dark matter with it through a process known as adiabatic contraction, effectively tightening the halo's grip and increasing its central concentration. The normal matter, through its complex physics, is sculpting the dark matter scaffold. On the opposite end of the scale, with the smallest dwarf galaxies, we often see the opposite problem. Many appear to have less concentrated halos than predicted, with those flat cores instead of dense cusps. This, as we have seen, could point to dark matter that is slightly warm, or to the explosive feedback from the first stars blowing out the center. Both ends of the spectrum suggest the same profound idea. The pristine, gravity-only story of halo formation is incomplete. The predicted mass concentration relation is the clean, theoretical baseline. The real universe scatters data points around that line, and each deviation is a clue. Is dark matter subtly interacting with itself, preventing the smallest halos from becoming as dense as they should? Or have the violent lives of stars and gas over billions of years repeatedly stirred and smoothed the dark matter, erasing the simple signature of its birth? This relation is more than a graph, it is a diagnostic tool. By measuring how real halos scatter from the predicted curve, we are reading the combined biography of dark matter and the luminous universe, a story of construction and disruption written in the language of gravity. The halo mass concentration relation charts the architecture of the universe, but at the very heart of that architecture lies a paradox of terrifying scale. Supermassive black holes, monsters weighing millions or even billions of times our Sun, squat at the center of nearly every large galaxy. Their existence is a chronological nightmare. We see them blazing in quasars when the universe was less than 1 billion years old, mere children in cosmic terms. How did they grow so massive so fast? The standard path to a black hole is through the death of a massive star, leaving behind a corpse of maybe 10 or 20 solar masses. To reach billions of solar masses from such a tiny seed in under 1 billion years is like trying to grow a redwood tree overnight from a mustard seed. The math simply does not work. There is not enough time for them to gorge on gas at the maximum possible rate. This forces a radical conclusion: these black holes were not born from stars. They were born giants, and their birthplace may have been the earliest, most pristine dark matter halos of all. This theory is called direct collapse. Imagine the universe just a few 100 million years after the Big Bang. The first dark matter halos are condensing out of the smooth primordial soup. Within one of these halos, a vast cloud of pure hydrogen and helium gas begins to fall inward, drawn by the halo's growing gravity. In a normal, later universe, this cloud would fragment as it cools. Dense knots would form, ignite as stars, and light up the halo. But in these specific early halos, conditions might have been perfectly sterile. There were no heavier elements, no metals, to help the gas cool efficiently. There was also no starlight yet to rip atoms apart. The gas remained relatively warm and stable. Under these unique conditions, the entire gigantic cloud, weighing perhaps 100,000 suns, could avoid fragmenting. It would collapse as a single, monstrous entity, not into a star but directly through its own weight, past any stable form, and into the oblivion of a black hole. In one swift, catastrophic event, a massive seed black hole is born, already tens of thousands of times heavier than any stellar remnant. This seed, planted in the dense center of a young dark matter halo, has a head start of cosmic proportions. It can then begin its epic feast on the surrounding gas, rapidly growing into the supermassive behemoths we see powering the early quasars. This idea creates a profound and intimate link between the largest and smallest things in our cosmic story. The dark matter halo, the largest gravitational structure, creates the specific environment that allows for the formation of the smallest conceivable object, a singularity. The halo is not just a container, it is a crucible. Its mass, its purity, its very isolation from the polluting effects of earlier stars might be the essential recipe for forging the central monster that will one day govern an entire galaxy's evolution. Yet this elegant theory is not without its own puzzles. Did these special, pristine halos exist in sufficient numbers to seed all the supermassive black holes we see? Or was direct collapse a rare cosmic event, leaving other black holes to find a different, even more mysterious path to greatness? The search is on to find the fingerprints of these direct collapse black holes in the deepest infrared images of the early universe, hunting for the moment when a dark matter halo first gave birth to darkness incarnate. Our own galactic home holds the ultimate dark matter crime scene, and the evidence is written in the motions of stars flung across the void. To map the Milky Way's invisible halo, astronomers have become celestial detectives, tracking the fastest and most far-flung objects they can find. Hypervelocity stars are their first witnesses. These are stars catapulted from the galactic center, likely by a close encounter with the supermassive black hole, now racing outward at speeds over 1 million miles per hour. Their trajectories are like probes fired deep into the dark matter halo. By measuring how these stars slow down as they climb out of the galaxy's gravitational well, scientists can weigh the halo's total pull. Then there are the ancient globular clusters, dense balls of hundreds of thousands of stars that orbit far beyond the galactic disk. Each cluster is a single point of mass moving under the halo's sole influence, its path a clean recording of the gravitational field at that distant location. Finally, the motions of satellite dwarf galaxies, like the Large and Small Magellanic Clouds, provide anchors at the very edges of our domain. By combining the data from all these traces, astronomers are piecing together a three-dimensional map of mass, not light. The central mystery of this map lies in its texture and form. Is the Milky Way's halo filled with the predicted hundreds of dense, lumpy subhalos, or is it surprisingly smooth? More fundamentally, what is its shape? Our simplest models often assume a spherical halo, but it could be squashed like an oblate spheroid, a cosmic beach ball, or stretched like a prolate spheroid, a giant football. The answer is a fossil record of our galaxy's violent history. Recent data from the Gaia mission has delivered a startling clue: our dark matter halo may be lopsided. The distribution and motions of stars and satellite galaxies suggest the invisible scaffold is tilted, warped, or off-center relative to the bright disk of the Milky Way. This is not what you would expect from a quiet, isolated evolution. Such a profound asymmetry is a classic signature of a major merger. It points to a dramatic event in our galaxy's past, like the collision with the Gaia Sausage Enceladus galaxy, a massive dwarf galaxy that plunged into the young Milky Way roughly 10 billion years ago. The gravitational shockwaves from that ancient cataclysm could have set the entire dark matter halo sloshing and tilting, a disturbance that has not yet settled. So the shape we measure today is not a pristine form, it is a still healing wound. Each hypervelocity star's path, each globular cluster's orbit, is a thread pulled through that distorted gravitational fabric. By tracing them, we are not just weighing a static halo, we are reconstructing the most violent chapter in our galaxy's biography, written in the language of invisible mass. The shape of our own halo is a relic of ancient collisions, but its true weight is measured by a much larger dance. Just beyond the frontier of the Milky Way lies our greatest cosmic companion, the Andromeda Galaxy. Together with a few dozen smaller galaxies, we form the local group, a small, gravitationally bound family adrift in the vast cosmic web. For decades, astronomers have used a beautifully simple idea, known as the timing argument, to weigh this entire family. It works like this: if you assume the Milky Way and Andromeda started very close together after the Big Bang and have been moving apart and then falling back together under their mutual gravity ever since, you can use their current separation and relative speed to calculate the total mass that must be pulling on them. It is a celestial version of throwing a ball into the air, knowing how high it went and how fast it is coming down, and from that deducing the strength of Earth's gravity. This elegant calculation gave us one of the first estimates for the mass of the local group, and it heavily implied the presence of dark matter long before the concept was mainstream. The mystery today is that this classic argument is now facing a crisis of precision. Modern satellites like Gaia have given us exquisitely accurate measurements of Andromeda's motion. We now know it is not heading straight for us but on a slightly sideways trajectory. More importantly, we have a much better map of the galaxies in our neighborhood. When we feed all this new, precise data into the timing argument, the numbers begin to strain. The simple two-body model starts to suggest a total mass for the local group that is puzzlingly low, or that the galaxies should be in a different configuration than we observe. This tension points to a profound oversight. The timing argument in its classic form treats the Milky Way and Andromeda as two simple points of mass. But we now know each is not a point, each is the luminous heart of an immense, sprawling dark matter halo that may extend over 1,000,000 light-years. These halos are not separate spheres that only touch when the galaxies collide. They are likely already overlapping, their faint outer edges mingling in the space between us. The gravitational dance is not between two stars but between two vast, diffuse clouds of invisible mass. To get the orbital math right, we may need to account for the full, extended distribution of these halos, their shapes, and how they interact long before the galaxies themselves ever meet. There is another, even more intriguing possibility. The cosmic web delivers matter along filaments, and the Milky Way and Andromeda sit at either end of a faint bridge of this web. Could there be a significant amount of dark matter and even diffuse gas still residing in that connecting filament, adding an extra gravitational tug that the simple model misses? Or perhaps the entire local group is embedded within a faint common halo, a vast mother structure of dark matter that formed first and within which all the member galaxies, including our two giants, later condensed. This would mean our halos are not entirely distinct, they are substructures within a greater dark hole. The timing argument's crisis is therefore a gift. It forces us to stop seeing our galaxy and Andromeda as isolated islands, and to view them as intertwined components of a single, complex gravitational system, where the invisible boundaries between halos are blurred, and the space between galaxies is not empty, but structured by the same dark architecture that built the galaxies themselves. The simple orbital math that once revealed dark matter now demands we understand its true, extended form. The gravitational dance between galaxies like ours and Andromeda shapes their dark matter halos, but the final result of that dance is written in light. Look at the night sky through a powerful telescope, and you will see a stunning gallery of galactic forms. Majestic spiral galaxies like our Milky Way, with their elegant, star-studded arms winding around a bright core. Smooth, football-shaped elliptical galaxies glowing with the soft, golden light of ancient stars, and scattered everywhere the small, misshapen, irregular dwarfs looking like cosmic splatters of starlight. This incredible diversity of structure, what astronomers call galaxy morphology, presents a deep mystery. Why does a dark matter halo, which is essentially just a spherical cloud of invisible mass, give rise to such a spectacular variety of visible forms? The connection between the simple, dark scaffold and the complex, luminous galaxy it hosts is one of the great stories of cosmic evolution. At the heart of this story is a concept called angular momentum. Think of a figure skater pulling in their arms to spin faster. As the primordial cloud of dark matter and normal gas begins to collapse under its own gravity billions of years ago, it has a tiny, initial bit of spin from the gentle tides of the early universe. As it collapses, that spin is conserved, causing it to rotate faster and faster, just like the skater. This rotation is crucial. It prevents the normal matter, the gas, from falling straight into the very center of the dark matter halo. Instead, the gas settles into a vast, flattened, rotating disk like pizza dough spinning into a flat crust. Within this disk, the gas can cool, fragment, and eventually ignite into stars, giving birth to a spiral galaxy. So the angular momentum of the collapsing dark matter halo acts as a cosmic sculptor, determining whether a beautiful disk can form. But this is only the beginning of the tale, because the universe is a violent place. A spiral galaxy's graceful disk is a delicate structure, and it can be utterly destroyed by a single catastrophic event, a major merger. When two dark matter halos of roughly equal size collide and merge, it is a disaster of cosmic proportions. The two central galaxies they host are pulled together by gravity, but they do not pass through each other like ghosts. Instead, their countless stars interact through complex gravitational tides, throwing each other onto wildly new orbits. The neat, orderly disk of a spiral is shredded, its stars scattered into a chaotic, three-dimensional swarm. The gas within both galaxies is violently compressed, triggering a firestorm of new star formation that quickly consumes all the available fuel. What emerges from this billion-year-long collision is no longer a spiral. It is an elliptical galaxy, a smooth, featureless ball of old, red stars with no disk and no active star formation. This transformation is one of the most profound predictions of our models, and we see it happening across the universe. But what happens to the dark matter halos during this violent merger? Remarkably, the dark matter, which only feels gravity, behaves quite differently than the stars and gas. During the collision, the two dark matter halos simply pass through one another and then settle back together, like two vast, ghostly clouds merging into one larger, slightly puffed-up cloud. They do not experience the friction and violent compression that the normal matter does. This means the final elliptical galaxy resides within a dark matter halo that is more spherical and hotter, with its particles on more random orbits than the halo of its spiral predecessor. The galaxy's entire visible identity has been rewritten by the merger, but its dark matter halo merely bears a quieter, more statistical record of the event. Therefore, the morphology of a galaxy, whether it is a spiral, an elliptical, or an irregular dwarf, is not an accident. It is a direct fossil of its dark matter halo's personal history. A quiet, isolated halo that acquired its gas slowly and gently is likely to host a grand spiral. A halo that suffered a major merger in its past likely hosts an elliptical. The small, irregular dwarfs are often halos that were stripped of their gas early on, or that never managed to form a stable disk at all. Every time we classify a galaxy by its shape, we are reading the biography of its invisible foundation. The majestic spiral is a story of peaceful, ordered growth. The smooth elliptical is the scar tissue from an ancient, colossal violence. And in that visible scar, we can infer the unseen rearrangement of the dark matter that made it all possible. Spiral arms and elliptical cores tell the story of a galaxy's visible life, but they account for only a fraction of the normal matter the universe owes us. Cosmologists have performed a cosmic accounting of all the protons and neutrons, the baryons, created in the Big Bang. When they tally up all the stars, gas, and dust in galaxies like our own, the numbers come up short, dramatically short. Up to half of all the normal matter in the universe is simply missing from the places we expect to find it. This is the mystery of the missing baryons, and the prime suspect for their hiding place is the one structure vast enough to conceal them, the dark matter halo itself. We are not searching for cold gas or stars, but for a seething million-degree atmosphere known as the circumgalactic medium, a vast corona of hot gas that may envelop every galaxy like ours. This halo of hot gas would be the final reservoir in the Great Baryon Cycle, the place where matter waits before falling into fuel star formation, or where it is expelled to after a supernova blast. Finding it is like trying to map the invisible breadth of a galaxy. The primary tool for this hunt is not a telescope that captures light, but one that dissects it. Astronomers train their instruments on brilliant, distant quasars, the luminous cores of ancient galaxies. As the quasar's light travels billions of light years to reach us, it passes through the circumgalactic medium of any foreground galaxy that lies in its path. The hot gas in that halo does not glow brightly enough to see directly, but it leaves a fingerprint. Specific atoms within the hot gas, like oxygen, nitrogen, and neon, absorb very particular wavelengths of the quasar's brilliant light. This creates dark, narrow lines in the quasar's otherwise smooth spectrum, like unique barcodes imprinted by the invisible halo. By analyzing the pattern, depth, and width of these absorption lines, scientists can determine the composition, temperature, density, and even the velocity of this elusive gas. It is an autopsy performed on a ghost using a distant beacon as the surgical light. Recent observations have confirmed that this hot, diffuse corona does indeed exist, extending for hundreds of thousands of light-years around galaxies like the Milky Way. It contains a staggering amount of mass, potentially enough to solve a large part of the missing baryon problem, but this discovery only deepens the mystery. How does this hot gas get there, and what is its fate? Some of it may be pristine material, ancient hydrogen and helium that fell into the dark matter halo from the cosmic web, but was heated to extreme temperatures as it crashed in. Other parts of the corona may be recycled material, gas that was blown out of the galaxy by supernova winds or active black holes, now lingering in the halo before it cools and rains back down in a process called galactic fountain. The circumgalactic medium is not a static shroud. It is a dynamic, churning interface between a galaxy and the cosmic void. Its properties hold the key to understanding why some galaxies form stars vigorously while others lie dormant. A halo with a hot, massive corona might act as a pressure cooker, preventing new gas from cooling and falling in, effectively quenching star formation. A cooler, clumpier corona might allow for steady accretion, fueling a galaxy for billions of years. The dark matter halo defines the gravitational theater, but it is the behavior of this hot, normal matter within it that may write the final act for the galaxy's luminous future. We are now mapping this hidden ocean of plasma, learning that the space between galaxies is not empty, but filled with the faint, hot breath of the dark matter halos themselves, a breath that holds the missing pages of our cosmic ledger. The hot breath of galactic halos connects us to the local universe, but the story of dark matter is written across the entirety of cosmic history. A fundamental crisis now grips cosmology, one that threatens to reshape our understanding of everything from the first instant to the present day. It is called the Hubble tension, and it is a direct disagreement over the expansion rate of the universe itself. On one side, we have the pristine snapshot of the infant cosmos, the cosmic microwave background radiation. By meticulously analyzing the subtle patterns in this ancient light, we can predict how fast the universe should be expanding today. On the other side, we have direct measurements in our local universe using brilliant stars and exploding supernova as mile markers. These two methods, both exquisitely precise, yield stubbornly different answers. The universe appears to be expanding faster nearby than the early universe says it should. This is not a small error. It is a significant discrepancy that has survived over a decade of increasingly careful scrutiny. It suggests something profound is missing from our standard model of cosmology, lambda cold dark matter. One of the most compelling proposals to solve this tension invokes a new form of energy that briefly flickered to life in the universe's first few 100,000 years. Scientists call it early dark energy. This is not the dark energy we know today, which drives the universe's accelerated expansion. This would be a transient burst, an extra push that slightly changed how the universe evolved during that critical, formative era. The implications for dark matter halos are immense. The growth of these invisible structures is exquisitely sensitive to the expansion history of the cosmos. If early dark energy gave the universe an extra nudge, it would have altered the timeline. It might have delayed the moment when dark matter could begin to clump under its own gravity. Think of trying to build a sandcastle as the tide is coming in. If the water rises faster, you have less time to pile the sand before it gets washed away. Early dark energy could have acted like a faster rising tide, slightly postponing the start of halo construction. The halos would have gotten a later start, and that delay would leave a permanent signature in their population. There would be fewer of the very oldest, most massive halos in the universe than our standard models predict. This is where a new kind of cosmic detective work begins. Could we use dark matter halos themselves as a clock to test this idea? By counting the number of massive galaxy clusters which sit in the most massive halos across different epochs of cosmic time, we could measure the speed of structure growth. If we find fewer colossal clusters in the early universe than expected, it could be the smoking gun for early dark energy or a similar modification, but we cannot see the halos directly. We see the galaxies that light them up, and the relationship between halo mass and galaxy brightness is messy and complex. This forces astronomers to become cosmic archaeologists, using gravitational lensing and the observed properties of galaxies to statistically weigh the invisible halos they inhabit, building a census of halo masses across billions of years. The Hubble tension, therefore, is no longer just a debate about expansion speeds on a graph. It is a call to map the invisible architecture of the universe with unprecedented precision, from the present day back to its first structures. The dark matter halo, long the mysterious foundation of galaxies, may now hold the key to resolving the most pressing crisis in modern cosmology. Its growth history is a hidden record of the universe's true expansion story, waiting to be read. The Hubble tension pushes us to question the very fabric of our cosmic model, and that questioning inevitably leads us back to the identity of the dark matter particle itself. For decades, the spotlight has been fixed on one leading candidate, the WIMP, the heavy, slow-moving particle that interacts through the weak force. But the persistent silence from direct detection experiments and the puzzling galactic core signals have opened the door for a radically different contender, one that would rewrite the rules of the dark matter halo from the ground up. This is the axion. If the WIMP is a cosmic boulder, the axion is a whisper of a particle billions of times lighter. At such a tiny mass, quantum mechanics dictates its behavior would be less like a discrete particle and more like a diffuse, coherent wave on scales as vast as a galaxy. This single shift in perspective unravels a cascade of mysteries for halo structure. Because axions are so light and so numerous, they would naturally collapse into a state known as a Bose-Einstein condensate, a quantum phenomenon where countless particles behave as a single coherent wave. In the heart of a dark matter halo, this condensate could stabilize into a dense, stable ball called a solitonic core. Unlike the sharp, steep cusp predicted for WIMP, this solitonic core would have a flat central density, exactly the kind of feature astronomers infer when they observe the rotation curves of dwarf galaxies. The axion, therefore, offers an elegant, built-in solution to the cusp versus core controversy, not through astrophysical feedback, but through the intrinsic quantum wave nature of the dark matter itself. The implications grow even stranger. A halo made of axion waves would not be a static cloud. It could exhibit intricate interference patterns like ripples on a pond, creating subtle density waves throughout its structure. Furthermore, dense knots of this wave-like matter could pinch off to form self-bound objects called axion stars, potentially floating within the larger halo like invisible quantum froth. These stars would not burn with nuclear fire, they would be held together by their own wave function, and if they grew too massive, they could theoretically collapse in a burst of radio waves. This means experiments hunting for axions are doing far more than searching for a new particle. They are testing a very specific blueprint for the inner architecture of dark matter halos. Laboratories around the world are using powerful magnetic fields to try and convert these hypothetical axion waves into faint photons, a process called the Primakov effect. Others are looking for the distinctive spin patterns axions would impart on distant starlight. Each null result narrows the possible properties of the axion, and in doing so, rules out a specific set of predictions for how our galaxy's dark matter core should be structured. The axion hypothesis transforms the halo from a gravitational scaffold into a quantum object of cosmic scale, where the rules of the very small dictate the form of the very large. The quantum wave of an axion halo is a profound departure from the simple, silent particle, but it is not the only way to give dark matter a hidden social life. There is a more direct, more forceful possibility. What if dark matter particles do not just pass through each other like ghosts, but can actually bump, scatter, or even annihilate? This is the radical proposal of self-interacting dark matter, often called SIDM. It suggests dark matter feels a new force, one that works only within the dark sector itself. The implications for the structure of halos would be immediate and dramatic. In the dense, crowded centers of galaxies and dwarf galaxies, these particles would constantly interact. Just like air molecules in a room, collisions would transfer energy from the fastest-moving particles to the slower ones. Over cosmic time, this process would smooth out the distribution. The sharp, dense peak of a cusp would be eroded, its energy redistributed outward, naturally forming the flat, constant density cores that astronomers so often observe in dwarf galaxies. It is an elegant one-step solution. The dark matter, through its own internal physics, sculpts itself into the right shape. This idea directly challenges the need for complex astrophysical feedback from supernova to explain those cores. Instead of stars blowing out the dark matter simply settles itself, but the power of self-interaction does not stop at the core. It could also explain the overall shapes of halos. In the standard cold dark matter model, halos are predicted to be slightly flattened like a squashed beach ball due to their rotation. But if dark matter particles scatter, they act like a fluid with a kind of pressure or viscosity. This can make the inner regions of a halo more spherical, almost like a droplet of liquid balancing its own surface tension against gravity. The halo's shape becomes a direct clue to the strength of the dark force. So how do we test for something that only interacts with itself? We need to watch dark matter in a cosmic collision, a place where its behavior is starkly separated from normal matter. The most famous laboratory for this is the Bullet Cluster. This is not a single object, but two galaxy clusters that have violently smashed through one another. The collision was so immense it ripped apart the components of each cluster. The hot gas, the normal matter that glows in X-rays, was slowed and heated by the impact, like two clouds of smoke colliding and mingling. But the dark matter, inferred from gravitational lensing maps, did something astonishing. It sailed right through the collision, largely unaffected, ending up in two distinct clumps far ahead of the stalled gas. This clean separation was hailed as definitive proof that dark matter exists and is collisionless. But for scientists hunting for self-interactions, the Bullet Cluster offers a more subtle test. If dark matter particles do scatter, even very weakly, they would not pass through each other completely unscathed. There would be a slight drag, a hesitation. The dark matter clumps might lag a little behind or be slightly offset from the positions of the galaxies they host. The current data shows no significant offset, placing an incredibly tight limit on how strongly dark matter can interact. It must be almost, but not perfectly, collisionless. This limit is a puzzle. It suggests that if self-interacting dark matter is real, the force must be exquisitely tuned, strong enough to reshape dwarf galaxy cores over billions of years, yet weak enough to be invisible in the furious collision of the Bullet Cluster. Can one model satisfy both extremes? Some theorists propose a solution where the interaction is velocity-dependent. In the cold, slow-moving environment of a dwarf galaxy core, particles would interact more often. In the fast-moving, high-energy chaos of a cluster collision, they would simply zip past each other too quickly to notice. This delicate balance makes SIDM a compelling but challenging mystery. It offers a beautiful simplicity for explaining the cores of dwarf galaxies, but it demands a new particle with very specific, fine-tuned properties. The hunt is now on to find even more extreme cosmic collisions, or to study the detailed shapes of thousands of halos. searching for the subtle signature of a dark matter particle that is not entirely alone in the universe. The idea of self-interacting particles redefines dark matter's social life, but what if the particles themselves are not particles at all? One of the most audacious proposals in cosmology suggests that dark matter halos might be made of black holes. Not the supermassive giants at galactic centers, but trillions upon trillions of tiny, ancient singularities, each perhaps no heavier than a large asteroid or a small planet. These would be primordial black holes, not born from dying stars, but forged in the unimaginable density of the universe's first second of existence. In this radical vision, the vast diffuse halo of our galaxy is not a cloud of unknown particles, but a colossal swarm of these microscopic cosmic fossils. The halo becomes an immense hive of gravitational singularities, each a pinprick of infinite density left over from the Big Bang itself. This idea elegantly sidesteps the need to invent a new, never-seen particle by proposing that dark matter is made of the most extreme objects gravity can already create. The mystery, then, is not what dark matter is, but whether such a population of ancient black holes could possibly exist without us having noticed. How do you hunt for black holes the size of mountains scattered across light years of space? The primary tool is a phenomenon called gravitational microlensing. If a primordial black hole drifts precisely between Earth and a distant star, its gravity will act as a tiny lens, bending and focusing the star's light. For a brief period, that star will appear to brighten, then fade in a characteristic symmetric curve. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have monitored hundreds of millions of stars for decades, searching for these telltale flashes. They have found microlensing events, but not nearly enough to account for all dark matter if it were made of black holes in the most likely mass ranges. The data places severe limits, suggesting that while some primordial black holes might exist, they cannot be the sole constituent of the halos. They would be a minority population, not the dark matter majority. Other constraints come from the delicate fabric of the early universe. A vast swarm of compact, heavy objects in the first few 100,000 years would have left scars on the cosmic microwave background. Their gravity would have subtly heated the primordial plasma, creating distinctive patterns in the ancient light that we do not observe. Furthermore, these black holes would act like gravitational wrecking balls within fragile dwarf galaxies. If dark matter halos were made of dense, point-like objects, they would constantly be stirring up and perturbing the orbits of stars in these small, faint galaxies. Over time, this gravitational heating would puff up the dwarfs, making them larger and more diffuse than what we actually see. The observed stability of dwarf galaxy stellar populations argues against a halo filled with a large number of compact asteroid mass objects. So where does this leave the idea? It pushes the possible mass range for primordial black hole dark matter into either extremely low masses, far smaller than an asteroid, or into a narrow, higher mass window around the mass of a large planet. These windows are not yet fully closed, keeping the possibility alive on the fringes of cosmology. This fringe idea forces a profound shift in perspective. It asks us to reimagine the dark matter halo not as a substance, but as a demographic, a census of countless invisible corpses from the birth of time. Each hypothetical primordial black hole is a relic of a quantum fluctuation so violent it collapsed the fabric of space itself in an instant. The halo becomes a graveyard of singularities, a collective gravity so vast it binds galaxies, yet sourced by entities so small they defy our vision. It is a reminder that in our quest to map the invisible, we must stay open to possibilities that sound like science fiction, for the universe has never been limited by our imagination. The cosmic dance of dark matter halos reaches its most dramatic climax not in solitude, but in a shattering embrace. When two galaxies are destined to merge, their invisible halos are the first to meet. Stunning supercomputer simulations reveal this encounter in ghostly detail. Two vast spherical clouds of dark matter, each containing a glittering disk of stars at its heart, begin to feel each other's gravitational pull. They draw closer, their outer fringes mingling like two breaths in cold air. Then they pass directly through one another. There is no crash, no explosion, no fiery collision. Because dark matter, as far as we know, interacts only through gravity, the countless particles in one halo simply stream past the particles in the other. They feel no friction, no drag, no force to slow them down. It is a perfectly dissipationless encounter. The halos emerge on the other side, slowed only by their mutual gravity, and then fall back together in a slow cosmic waltz, eventually merging into a single, larger, and slightly puffed-up dark matter halo. This ethereal pas-de-deux stands in stark, violent contrast to the fate of everything luminous within them. The normal matter, the stars and gas, experiences the universe in a completely different way. The stars, while also collisionless, are not smoothly distributed. They are discrete points of mass. As the two galaxies interpenetrate, their stars do not physically hit each other. The spaces between them are far too vast, but they do feel intense and complex gravitational tides. These tidal forces pull and stretch the galactic structures, throwing stars onto wild new orbits, utterly shredding the beautiful spiral disks. The gas, however, suffers the most dramatic transformation. It is a collisional fluid. The vast clouds of hydrogen and helium in each galaxy slam into each other at tremendous speeds. This direct impact creates immense shock waves, heating the gas to tens of millions of degrees until it glows not with starlight but with a fierce blaze of X-rays. The collision also triggers a firestorm of new star formation as the gas is violently compressed. This is the central mystery and the key signature. In a merger, the dark matter halos and the normal matter are brutally separated by their fundamental physics. The dark matter ghosts through the encounter, while the normal matter crashes, heats, and lights up. We have seen this signature written across the sky in one of the most famous cosmic snapshots, the Bullet Cluster. This is not a single object, but the aftermath of two galaxy clusters that have recently collided at unimaginable speed. Observations tell a clear two-part story. First, images from X-ray telescopes show the location of the hot, shocked gas, the normal matter. It lies in the center of the collision zone, a glowing, mangled cloud that was slowed and heated by the impact, just like the simulations predict. Second, maps created by measuring gravitational lensing reveal the location of the total mass, which is dominated by dark matter. These maps show two distinct, dense clumps of mass, each having sailed cleanly through the collision and now far ahead of the lagging gas. The mass and the light are in different places. This separation is considered some of the strongest direct evidence for the existence of dark matter as a distinct collisionless substance. It shows us that the halos are not just theoretical constructs. They are physical entities that behave in a specific, ghostly way, carrying the true weight of the universe through collisions while the luminous matter we see bears the scars. This behavior answers one question but raises another, more subtle one. If the halos pass through each other so cleanly, why do the merged galaxies we see today, the giant ellipticals, seem to sit in more spherical, relaxed dark matter halos? The answer lies in the aftermath. While the initial passage is ghostly, the halos are still bound by gravity. They fall back, oscillate, and eventually merge, their particles mixing through a process called violent relaxation. Over hundreds of millions of years, the new, combined halo settles into a smoother, more spherical configuration, a quiet testament to the colossal, invisible violence that formed it. The ghostly passage of colliding halos reveals a universe built on invisible architecture, but to understand its true nature, we must travel back to the very first moments of construction. In the darkness of the early cosmos, long before the first star flickered, the universe began to weave its most delicate threads. These were the earliest dark matter halos, structures of almost unimaginable smallness. While the halo enveloping our Milky Way holds the mass of 1 trillion suns, these first halos could have been as light as a single planet Earth or even less. They are called microhalos, and they are the primordial seeds from which all larger structure grew. Forming when the universe was only a few 100 million years old, they are the cosmic equivalent of the first dust motes settling after a great explosion. Their existence is a cornerstone prediction of our standard cold dark matter model. As the universe expanded and cooled from the Big Bang, the densest ripples in the primordial dark matter soup were the first to collapse under their own gravity. These microhalos would have been the universe's very first gravitationally bound structures, the foundational bricks in a cosmic pyramid scheme, merging over and over to build the galaxies we see today. The profound mystery is whether any of these ancient, pristine microhalos could have survived the ensuing 13.8 billion years of cosmic violence. If they did, they would be orbiting right now within the vast halo of our own Milky Way, like perfectly preserved fossils from the dawn of time. Finding one would be like discovering a living dinosaur, an unchanged relic of the universe's infancy. Their survival, however, is not guaranteed. It depends critically on a single property of dark matter, its primordial temperature. In the language of cosmology, dark matter is called cold if its particles moved slowly in the early universe and warm if they moved faster. If dark matter is warm, even slightly, those fast-moving particles would have washed out the smallest, densest ripples in the primordial soup. The microhalos would have been erased before they ever properly formed, like delicate sandcastles smoothed by an incoming tide. Therefore, the simple act of searching for microhalos becomes a direct test of dark matter's fundamental character. Are they out there, or did they never exist at all? The implications of their survival are staggering. A microhalo, having formed when the universe was hundreds of times denser than it is today, would itself be incredibly dense. If dark matter particles can annihilate each other, as many theories suggest, the rate of annihilation depends on the square of the density. Double the density and the annihilation signal quadruples. In a microhalo, the density could be millions of times greater than in the diffuse outskirts of our galaxy's main halo. This means a single, surviving microhalo could shine like a brilliant beacon in gamma rays, a pinprick of intense annihilation light against the dark sky. It would be the ultimate target for indirect detection, a signal so potent it might finally be unmistakable against the astrophysical background. Yet this also presents a paradox. If microhalos are so bright, why have we not already seen them? Their elusiveness deepens the puzzle. Perhaps they were not bright enough, or our telescopes have not yet looked in the right way. Or more intriguingly, perhaps they were destroyed. Even if they formed, the journey into a modern galaxy like the Milky Way would have been perilous. As microhalos were swallowed by larger and larger halos over cosmic time, they would have been subjected to intense tidal forces. The gravitational pull from stars and other dark matter clumps could have shredded them, stripping away their outer layers and perhaps destroying them completely. Their survival is a delicate balance between their innate density and the violence of their environment. The hunt for microhalos is thus a hunt for shadows within a shadow. We cannot see them directly, but we can look for their potential gamma-ray glow with space telescopes, or search for the subtle gravitational effects they might have on the thin streams of stars orbiting our galaxy. Their presence or absence will tell us if dark matter is truly cold, and if the universe built its grand design from the smallest possible seeds. They are the hidden ancestors of our galactic home, and finding even one would give us a direct glimpse into the universe's first dark, silent structures. The hunt for microhalos is a search for the universe's first whispers, but to understand their ultimate destiny, we must zoom out to a scale so vast it defies human intuition. The dark matter halo of a single galaxy is not an isolated island in an empty sea. It is a single, luminous knot in the grandest structure known to exist, the cosmic web. Picture the universe not as a scattering of galaxies in blackness, but as a colossal, three-dimensional spiderweb spun from dark matter. Vast, thread-like filaments of invisible mass stretch for hundreds of millions of light years, connecting dense clusters of galaxies at their intersections. Between these filaments lie unimaginably empty voids, cosmic deserts spanning distances so great light takes eons to cross them. This is the true architecture of our cosmos, and every dark matter halo, from the mightiest cluster to the faintest dwarf, is a bead strung upon its threads. The central mystery here is one of cosmic connection. How does a halo's specific address within this web determine its entire life story, its mass, its spin, and its fate? The web is not just a backdrop, it is the blueprint. Consider the spin of a galaxy. Where does a trillion suns find the momentum to rotate? The answer may be woven into the filaments themselves. As dark matter and gas flow from the voids into the filaments, and then stream along those filaments toward the waiting halos at the intersections, these great rivers of matter do not flow straight. They twist and shear against each other, imparting a tidal torque, a kind of gravitational twist. This process can set the entire collapsing halo spinning. Remarkably, simulations suggest this spin is not random. Halos that form along the same cosmic filament may share a preferred spin direction, their axes of rotation aligned with the filament like beads spinning on a string. This would mean the majestic rotation of a spiral galaxy is not an accident of its local collapse, but is imprinted upon it by the large-scale flow of the entire universe, a memory of its birthplace in the web written in the motion of its stars. But the web does more than just spin halos, it feeds them. The filaments are not empty threads, they are the universe's supply lines, conduits of pristine hydrogen and helium gas that have flowed since the beginning of time. How and when this gas is delivered to a halo is the single most important factor in determining what kind of galaxy forms within it. A halo sitting at a busy intersection of multiple thick filaments, like a city at a major highway junction, will receive a steady, rich influx of cold gas. This bounty fuels rapid and sustained star formation, potentially building a brilliant, star-rich spiral. A halo perched on a thinner, more isolated filament, however, may receive only a trickle. Its growth is stunted, its star formation sporadic, leading perhaps to a smaller or more quiescent galaxy. The web dictates the menu, and the halo must dine on what is delivered. This control extends to the most violent events in a galaxy's life, mergers. The cosmic web orchestrates the dance of halos. Two halos that form along the same dense filament are fated to be drawn together along that gravitational highway, eventually merging in a colossal collision that can transform two spirals into an elliptical. A halo that forms in a more sparsely populated region of the web may live a quiet, isolated life, untouched by major mergers for billions of years, preserving its delicate disk. The web, therefore, is both a builder and a destroyer. It gathers the material to construct galaxies, and it arranges the collisions that tear them apart and rebuild them into new forms. This grand perspective reveals the ultimate interdependence of the cosmos. The properties of the dark matter halo that cradles our Milky Way, its mass, its spin, its history of quiet growth, are not solely its own. They are a direct consequence of our specific place in the cosmic web, a location determined by the random quantum fluctuations of the Big Bang amplified over 13.8 billion years. The filament we reside upon, the voids that border us, the neighboring clusters that pull on us, all have subtly shaped our invisible foundation. To understand a single galaxy, we must first map the invisible continent upon which it sits, tracing the dark rivers that fed it and the gravitational geography that shaped its destiny. The halo is the node, but the web is the story. The cosmic web weaves a tapestry of both light and profound darkness, and within its vast expanse may lie the ultimate expression of the dark matter halo's independence. These are the empty halos, structures of immense gravitational power that have never ignited a single star. They are the true dark galaxies, pure dark matter halos that have, for reasons unknown, completely failed at the task of galaxy formation. Their existence is a logical endpoint of our theories. If dark matter forms first and normal matter falls in later, then there must be places where that second step never happened. The mystery is not just whether they are out there, but how we could ever hope to see something that emits no light at all. We have already glimpsed possible shadows of these phantoms. Astronomers have long used radio telescopes to map clouds of neutral hydrogen gas, the raw fuel for stars, by detecting the faint radio whisper emitted when its electron spins flip. Occasionally, they find clouds that are massive, rotating, and clearly held together by gravity, but which show no trace of stars in even the deepest optical images. These are called HI dark clouds, where HI stands for neutral hydrogen. They appear to be dark matter halos that manage to acquire a cloak of gas, but for some reason, that gas never fragmented and collapsed to form stars. Perhaps the cloud is too diffuse, its internal pressures too low to trigger collapse. Or maybe it exists in a harsh environment where an external source of ultraviolet radiation keeps the gas just warm enough to resist cooling and condensing. These objects are tantalizing, but they are not completely dark. They still possess that thin shroud of detectable gas, a luminous clue to their invisible mass. The hunt for a truly pristine, starless halo requires a more ghostly method, one that bypasses light entirely. This is where gravitational lensing becomes our most powerful tool. When a massive object passes directly in front of a distant star or galaxy, its gravity bends and magnifies the background light. If that foreground object is completely dark, a massive halo with no stars or gas, the effect is the same. We would see a distant star suddenly and mysteriously brighten, then fade with a signature that indicates the lens is a single, extended object, not a point like a star. The challenge is monumental. We would need to monitor millions of stars continuously to catch such a rare alignment, and then we must rule out every other possible cause, such as a faint star or a rogue planet. Some intriguing lensing events have already been recorded that defy easy explanation, suggesting the presence of massive compact halo objects, or MACHO, drifting unseen through our galactic halo. While most of these are likely faint stars or stellar remnants, a few could, in theory, be the dense, cuspy cores of ancient, failed microhalos, the last surviving remnants of a completely dark structure. The ultimate prize, however, would be to lens an entire galaxy with a dark halo. Imagine a perfect, beautiful Einstein ring, a circle of distorted light from a background galaxy, but with absolutely nothing visible at the ring's center. No cluster of galaxies, no giant elliptical, just empty space. The ring itself would be the ghostly signature of a titanic concentration of invisible mass. A dark matter halo so massive it could host a galaxy, yet sitting in perfect emptiness. Such an object would be a dark galaxy in its purest form, a gravitational sculpture with no artist's signature. Finding one would be a transformative discovery. It would be direct, irrefutable evidence that dark matter halos are indeed the primary structures of the universe, and that the sparkling galaxies we see are merely optional decorations, fortunate accidents where the conditions for star formation were just right. It would confirm a profound and humbling hierarchy. Dark matter builds the houses, but lighting them up is a separate, fragile, and sometimes failed endeavor. The search for these empty halos is a search for the silent majority of the cosmos. The dark foundations upon which our illuminated world is merely a rare and brilliant exception. The search for empty halos forces us to confront the deepest assumption of all. For 24 mysteries, we have explored the dark matter halo as if it were a real thing, a substance made of unknown particles that clump under gravity to form an invisible scaffold. This entire grand narrative rests on one idea, that our theory of gravity, Einstein's masterpiece of general relativity, is perfectly correct on the scale of galaxies and the universe. But what if it is not? What if the dark matter halo is not an object at all, but a ghost, a gravitational illusion created by our own misunderstanding of how space, time, and mass truly interact? This is the final, most profound mystery, the ultimate nature of the cosmic dark matter halo. Is it a particle or a flaw in our equations? This alternative path has a name: modified Newtonian dynamics, or MOND. Proposed in the early 1980s by physicist Mordechai Milgrom, it starts from a stunningly simple premise. Instead of inventing a new, invisible form of matter to explain why stars at the edges of galaxies orbit too fast, perhaps we should modify the law of gravity itself, but only in places where gravity is exceptionally weak, like the vast outskirts of galaxies. Milgrom suggested that Newton's famous law of acceleration, force equals mass times acceleration, might need a tiny tweak. When accelerations become very, very small below a certain critical threshold, gravity could become stronger than Newton or Einstein predict. This single change, with no invisible particles, can perfectly reproduce the flat rotation curves of spiral galaxies and the tight radial acceleration relation we see. In the MOND view, there is no dark matter halo. The extra gravitational pull we attribute to it is simply gravity behaving in a new, unexpected way in the realm of the extremely faint. For decades, MOND was seen as a clever but fringe idea, a curve-fitting exercise that could not compete with the elegant, all-encompassing power of the particle dark matter model. But its persistence is due to one undeniable fact. It predicts galactic rotation curves with astonishing accuracy, using only the visible mass of stars and gas. Where the standard model must carefully tune the distribution of an invisible halo to match each galaxy, MOND often gets it right on the first try. This predictive success is a constant thorn in the side of the mainstream. However, MOND in its original form is not a complete theory. It is a mathematical prescription for a specific situation, not a fundamental rewrite of physics that can explain the cosmos from the Big Bang to the present day. This is where a more ambitious theory enters: tensor vector scalar gravity, or TVS. Developed by physicist Jacob Bekenstein, TVS is a full-fledged relativistic theory, a competitor to Einstein's general relativity that incorporates MOND ideas at its core. In TVS, gravity is not just the curvature of spacetime by mass and energy. It is mediated by multiple fields, a tensor field like Einstein's, plus a vector field and a scalar field. This more complex interaction naturally produces stronger gravity in low acceleration environments, potentially mimicking the effects of dark matter without requiring it. In this geometric picture, what we call a dark matter halo is not a cloud of particles, but a subtle alteration in the gravitational field surrounding a galaxy, a permanent warp in spacetime dictated by the visible mass alone. The grand showdown, then, is between two radically different visions of reality. In one universe, dark matter halos are real, physical structures made of a new particle that constitutes 85% of all matter in the cosmos. This particle shaped the early universe, guided the formation of galaxies, and now holds them together. Its discovery would open a portal into a completely unknown sector of physics, a dark universe parallel to our own. In the other universe, dark matter halos are mirages. They are the gravitational shadows cast by a deeper law of nature, a law where gravity itself has a hidden face that only reveals itself in the deep quiet of interstellar space. The halo is not a thing you could ever touch or detect directly. It is a symptom of our incomplete knowledge. How do we decide? The battle is fought on the field of predictions. The standard lambda-cold dark matter model has a towering success. It explains the large-scale structure of the universe, the patterns in the cosmic microwave background, and the evolution of galaxy clusters with remarkable precision. It provides a single, unified framework that works from the largest scales of the cosmic web down to the scale of individual galaxies, though with the persistent small-scale tensions we have discussed. Modified gravity theories like TVS struggle to match this cosmological success without adding some form of dark matter-like component, which to many defeats their original purpose. Yet, they point to places where the particle model seems to require astonishing cosmic coincidences, like the perfect correlation between visible mass and gravitational strength in the radial acceleration relation. For particle dark matter, this is a puzzle to be solved. For MOND, it is the fundamental law. Perhaps the most telling tests come from environments where the two theories make starkly different predictions. Consider two galaxies colliding like the bullet cluster. In the particle dark matter model, the collisionless dark matter halos sail through each other, separating from the slowed collisional gas exactly as observed. For a pure modified gravity theory, the gravity is tied to the visible mass, the stars and gas. Since the stars are also collisionless and pass through, their gravity should stay with them. But the gas, which contains most of the visible mass in a cluster, gets stuck in the middle. Modified gravity would therefore predict the strongest gravitational lensing, the place where mass is, to be in the center with the gas, not out with the galaxies. The observed lensing maps, which show the mass with the galaxies, are a severe challenge for unmodified MOND. Proponents of modified gravity work to adjust their theories to account for such events, often by invoking new fields or particles, blurring the line between the two paradigms. This final mystery is not merely academic. It asks us what kind of universe we live in. Is it a universe filled with hidden, exotic particles waiting to be discovered in a lab, a universe of profound material richness? Or is it a universe governed by a more intricate and subtle geometry than Einstein imagined, where the force that shapes the cosmos has layers we have only begun to peel back? The dark matter halo sits at the center of this question. Every observation of a rotating galaxy, every distorted image from gravitational lensing, every simulation of cosmic evolution is a piece of evidence in this ultimate trial. We have spent decades mapping the properties of these halos, their masses, their shapes, their interactions, searching for the clue that will break the tie. The answer will not just tell us what holds galaxies together, it will reveal whether the cosmos is built mostly from something we have never seen, or from a deeper truth about the fabric of space and time that we have yet to fully comprehend. The halo's greatest secret may be that it is forcing us to choose between two different kinds of revolution, and the choice will redefine our place in the dark. 25 mysteries, each a different window into the same profound darkness. From the silent absence of hundreds of dwarf satellites to the ghostly perfection of ultra-diffuse galaxies, from the warped planes of orbiting companions to the eerie harmony of the radial acceleration relation, every puzzle points toward a single, inescapable conclusion. The cosmic dark matter halo is not a simple, static mass. It is a dynamic and complex entity, an architect and an archive. Its invisible structure dictates how galaxies are born, how they spin, and whether they blaze with starlight or fade into obscurity. Its history is written in the sloshing motion of tidal streams and the tilted orbits of ancient stars, a biography of violence and quiet growth spanning billions of years. The very shape of these halos may hold the answer to the universe's accelerating expansion, and their smallest, earliest seeds could tell us if dark matter is a wave, a particle, or something beyond our current imagination. This is far more than a missing piece in a cosmic ledger. It is the hidden framework of reality itself, the scaffolding upon which every galaxy, every star, and every planet is built. The journey through these mysteries reveals a universe where the unseen commands the seen, where darkness is not an emptiness but a substance of immense power and subtlety. And the story is far from over. The next great revelation might come from the piercing gaze of the James Webb Space Telescope peering into the earliest halos, from a supercomputer simulation that finally reconciles cusps and cores, or from a sudden flash of insight in a laboratory here on Earth. It could even come from you. Which of these 25 mysteries captures your imagination the most? Is it the ghostly galaxies made almost entirely of dark matter, or the quantum possibility of an axion wave flowing through the cosmos? Share your thoughts below and join us as we continue to explore the greatest edges of space and science. The universe's darkest secret is still waiting to be